Good day, respected examiner and Dr. Chen. My name is He Junlei. Today, I'm presenting my analytics lab project titled Predicting E-commerce Customer Satisfaction, a machine learning approach using domain-driven optional features. In today's highly competitive digital market, keeping customers is more important than ever. My research focuses on how we can use machine learning to predict and prevent customer dissatisfaction before it hurts the brand's reputation. To solve this problem, I created a workflow called the SOPPR framework. This stands for Simplified, Optionally, Prediction, Prescriptive, Recovery. Traditionally, e-commerce platforms handle angry customers passively. They wait for a one-star review to appear, and then they apologize. But by that time, the customer is already lost. The SOPPR framework shifts our focus from passive reviews to active, machine learning-based alerts. It allows us to spot high-risk orders in real time. Before building the model, we must face some major data challenges in the massive Brazilian OList dataset. First, there is a huge data imbalance. Satisfied customers greatly outnumber unhappy ones by roughly 76.5% to 23.5%. Second, many researchers try to fix this by using fake data generation methods like smooth. However, adding fake customers data can hide the true patterns of real retail sales. Lastly, many modern models are overly complex black boxes. They are just too hard for managers to understand quickly. Therefore, my goal is to build a clear, reliable model that captures service failures using a simple set of business features. This brings me to my core research objectives. Objective 1 is to find the key business drivers for customer satisfaction. I deliberately keep the model simple and focused on three actionable metrics: product price, price value, and delivery delay. Objective 2 is to compare advanced three models against standard models when facing severe data imbalance. And finally, objective 3 is to turn this mathematical prediction into practical service recovery plans for e-commerce managers. To achieve this, my methodology has four phases. Phase 1 was data collection, where I gathered over 114,000 transaction records for all lists. Phase 2 was data cleaning. I used the median values to fill missing data and narrowed the focus strictly to our three core features to keep the model fast and clear. Phase 3 was the modeling stage. I used an 80 to 23 test split. More importantly, I applied class whittling to force the models to pay extra attention to the minority group, the dissatisfied customers. Phase 4 was evaluation. I prioritized the metrics like F1 score and the minority recall over stand global accuracy. I carefully tested seven different classification models. First, I tested standard models like logistic regression, k-nearest neighbors, and net basis to establish a baseline. Then I moved to tree models like decision trees and random forest to capture complex business patterns. Finally, I used advanced boosting models, namely XGBoost and LightGBM, to push the limits of predictive accuracy on large-scale data. Now we come to the most critical findings of my research. If you look at the top left box, the initial test revealed a very dangerous trick, the accuracy paradox. When running standard models, we achieved a very impressive global accuracy of 76.2%. However, the minority recall was a very low 7.18%. What does this mean? The model readily guessed that every customer would be satisfied. As highlighted in red, the business impact is fatal. The system completely missed nearly 93% of genuinely unhappy customers. This proves the relying only on overall accuracy is highly misleading. To fix this build spot, as shown on the bottom left, I introduced the cost-sensitive class within to force the models to focus on the minority class. Now, please direct your attention to the performance table on the right. The improvement is clear. The weighted random forest emerged as the most balanced model overall, achieving an F1 score of 0.5111 and an ROC-AC of 0.7231. We successfully captured nearly 45% of actual service failures without generating any fake data. It is also worth noting that the weighted decision tree achieved the highest record at 0.5142. While predicting human feelings is naturally difficult, these results prove the three business models are vastly superior to simple layer models in handling highly imbalanced retail data. Addressing my first objective, I used the LightGBM model to extract the importance of each feature. The results were surprising. Unexpectedly, freight value ranked higher than the base product price as the strongest driver of customer dissatisfaction. This shows the online shoppers are extremely sensitive to secondary shipping costs. Checkout shock from high delivery fees acts as a major trigger for customer anger and one-star review. I also conducted a detailed threshold analysis on our time variable, delivery delay. This chart shows how the risk of churn jumps as delays increase. When packages arrive on time, the baseline dissatisfaction rate is roughly 25%. However, a minor delay of just 1 to 3 days enters the initial friction zone, where dissatisfaction jumps to nearly 49%. Crucially, once a delay passes the 4-day mark, it enters the high-risk zone, where a massive 78.3% of customers leave negative feedback. This 4-day mark is a critical warning line for management. Before concluding, it is important to acknowledge the limitations of this study. First, our findings are based on a single Brazilian dataset. This means the 4-day risk rule needs to be tested in other global markets before wide use. Second, to keep our model highly efficient, we excluded test reviews and customer locations. In the future, researchers could combine test sentiment analysis with our numerical model to make the prediction even stronger. In conclusion, this research shows that we can predict customer feelings using a simple set of business features. Based on the data, I propose 3 practical strategies. First, implement a dynamic shipping subsidy because high freight values strongly drive anger. Platforms should prioritize reduced shipping costs for vulnerable orders rather than just discounting the product. Second, deploy an automatic 4-day protocol. If the tracking system detects an order well past the 4-day delay mark, the platform should automatically refund this shipping fee to calm the customer down before they write a bad review. Third, we can use these insights to evaluate and optimize our logistics partners. By shifting from passive apologies to active, data-driven service recovery, platforms can protect their reputation and keep their customers. Thank you, Dr. Wei Chen and the examiner, for your time today. This concludes my presentation.